Welcome to the next video for Biochemistry 1. This video is addressing the basic concepts of substrate binding to enzymes. And so the topics actually that we are going to discuss today are going to include enzyme reaction steps. So we'll talk about the actual steps that are involved in an enzymatic reaction. We'll talk about the models of substrate binding and enzyme specificity, so the types of specificity that enzymes show. Then we're going to talk about a specific one of those types that is called stereochemical specificity. And so we'll talk a little bit about that, and then I'll give you two examples of some racemic drugs to illustrate the importance of stereochemical specificity. And then we'll talk about the two models of enzyme regulation. Okay, so we're going to go ahead and dive in and get started. I know you're excited. Here we go. Okay, so first we're going to talk about the steps involved in an enzymatic reaction. And those steps include the first step is the substrate, of course. And remember, when you're talking about enzymes, we don't talk about reactants. We talk about substrates. So the chemical species, or the thing that's converted to product when you're talking about enzymes, that would be considered the reactant if you were talking about a general just kind of chemistry reaction, is instead referred to as the substrate. So it's represented by an S here. So in the first step of an enzymatic reaction, the enzyme has to bind the substrate, okay, and that step results in the formation of an enzyme substrate complex, okay. Then step 2 involves the formation of what is called the transition state, and sometimes the transition state is designated as a double hash mark, double whatever that thing is called. And the transition state is extraordinarily important, and we're going to talk a lot about it in detail. And what it is a chemically unstable species that is usually thought of as a hybrid between the substrate and the product. So it's not substrate, it's not product. It is what you get on the way to making product out of that substrate. The key about this, though, the thing that's most important, is that it is always, always, always a chemically unstable species. So we'll talk more about that later. Step 3 involves the conversion of that transition state into product. Okay, so then product is made, and then step 4, of course, you have to release that product from the enzyme. Now that seems maybe kind of trivial, but it's really not, because for an enzyme to be a catalyst, one of the characteristics of a catalyst is that it has to be regenerated. So the product has to come off of the enzyme so that the enzyme then can be returned to its original active state, and it can come back and bind more more substrate and go through this reaction again. Okay, so the rest of this slide really is just restating what I just said to you in words, and then down here in pictures, just in case you understand either one of those better than the general reaction scheme I provided up there. Okay, you should know these steps. You should know them like the back of your hand. Most of you probably are already familiar with them to some degree. So, okay, that was fast. We're going to move on to talking about the second topic, and we're going to talk about two different substrate binding models. So the thing that's kind of interesting about this, though, is that the truth, the reality, the real situation, again, kind of like the transition state, or kind of like resonance structures, the truth is really a spectrum upon which enzymes can lie. So at one end of that spectrum, you have one model, and at the other end of the spectrum, you have the other model. Okay, so this end you would have the first model we're going to talk about, which is the lock and key model, and down here you would have the induced fit model. Okay, so we're going to talk about this. Now, one of the things, though, that the spectrum kind of doesn't do well, thinking about substrate binding as a spectrum, is that once you leave the lock and key definition, you are induced fit. It's just the degree to which you're induced fit. So really, induced fit starts, pretty immediately there once you move away from the lock and key side. Okay, well, let me explain these so that maybe you'll understand a little bit better what I'm talking about here. And so we will talk about the first model, and the first model is indeed that lock and key model. You're probably taught this all the way up in your biology classes, in your kindergarten through 12th grade. Anytime you heard anything about enzymes, that's kind of funny to think that you'd hear about them in kindergarten. But when my daughter and my son were in kindergarten, I talked to their classes about enzymes, so it's possible that you did hear about them. Lock and key model involves, or it describes the process of substrate binding to the enzyme in the active site as a key fitting or inserting into a lock. Okay, so that's the idea of the lock and key model, and in that model, the substrate itself is a very rigid, it's got a very definite structure, like most substrates will. But the thing that's different, or the thing that kind of sets this model apart, is the rigidity of the active site of the enzyme. I know you can probably hear my dog barking in the background. She needs to be quiet. She's outside my backyard. Okay. So anyway, the active site of the enzyme is rigid and defined, and the substrate then, of course, fits into that active site like a key fitting into a lock. Okay, so in this model, the position of the residues, the amino acid side chains, in the active site of the enzyme are rigidly defined. And so you can imagine that if you change this substrate up just a little bit, it would not bind in this active site. It would be like trying to put the wrong puzzle piece into position. It just wouldn't quite fit. Okay, so what's going on here, though? You've probably heard of this before. What's going on here? What exactly are we talking about when we say the substrate fits into the active site? What do we mean by that? It's not just a physical steric kind of relationship like a key has with a lock. It's actually, if we were to take a piece of this active site and blow it up and look at the interactions that were happening between the substrate and the enzyme active site, then what would we see? Well, we would see all kinds of intermolecular interactions, right, between the amino acid side chains of the enzyme, of the substrate, interacting in a positive way with the amino acid side chains of the enzyme active site. Okay, so what kinds of interactions are we talking about there? Well, we're talking about salt bridges, like you might have between aspartic acid or glutamic acid and a lysine or an arginine there. You might be talking about hydrogen bonds that could exist between serines and even tyrosines or backbone atoms. You could be talking about nonpolar interactions, dispersion forces that would be present between, say, a phenylalanine ring and some valine here. Now you can see, so intermolecular interactions are where it's at when we're talking about what we mean when we say you have these kind of interactions, that the enzyme active site is rigid and it fits the substrate like a lock and a key do. So here you see how these, in addition to having these positive interactions placed exactly where they need to be, these favorable interactions, you also have steric considerations. So the substrate might bulge out like this, and you have this big bulky phenyl ring here on this phenylalanine, and the enzyme active site would have a pocket that phenylalanine would fit into. So it's not just intermolecular interactions, it's also sterics. And so the important thing really with this model of substrate binding is that you have very, very, very strong specificity. Okay, so the active site is rigid, and you almost always, I've never heard of a case actually, where you would have more than one substrate for an enzyme if the model of that enzyme's substrate binding is lock and key. And you can see why, because the interactions are such that you have to match exactly there. Oh, look, I wrote on that. You have to match exactly what's going on for this thing to fit. Now, luckily, actually, lucky for us that not all enzymes are like that. In fact, the vast majority don't fit this model. So the vast majority lie somewhere else on that spectrum. They lay somewhere between a little bit of induced fit all the way down here to being very, very loose fit in the way that they bind their substrate. So now we're going to talk about that second model that actually includes a lot more of the different kinds of enzymes will bind that in this model. Okay, so this is called the induced fit model, and with the induced fit model, it's different. Instead of like a lock and a key, you should think about this model as being more like a hand fits into a glove. Okay, so we know that many gloves, these are really horrible. Two different well, I was trying to show her two completely different types of hands here. This actually maybe looks like Gollum's hand from Lord of the Rings. I don't know what that is, but anyway, gloves are almost always one size fits all, right? So unless you have some sort of very strange monster hands of some kind, your hands will be able to fit in whatever gloves you buy. You don't have to get different sizes of gloves that would fit your particular hand. You don't have to be fitted for gloves. And that's because the glove actually conforms to your hand, and it can fit many different sizes and many different shapes of hands. In the induced fit model of substrate binding, it's the active site that conforms to the substrate. Okay, so here we go. Here's an example. So here I've drawn my enzyme. He looks, I don't know, kind of old, like he would have no teeth or something here, like an old enzyme. And get off my lawn or something. But that's not what I intended. He is very important here, even though he looks funny. So what this kind of floppy active site allows is the binding of different substrates that differ from each other. They can be different, and when they bind to this enzyme, the active site of that enzyme can close around, can conform to the shape of that substrate, regardless of, within reason, of course, regardless of the shape of that substrate. So this allows for an enzyme to work on, of course, I mean, you can tell just by what I just said, but it allows the enzyme to work on multiple substrates. Okay, and you can see that the further away from the lock and key model the enzyme is, the further toward that induced fit side, the more flexibility it would have and the more substrates it would be able to bind. Okay? Alright, so I'm going to switch to my second screen here. Okay, so now we're going to talk about enzyme specificity. And okay, except I can't get everything off. Okay, here we go. Enzyme specificity. Okay, so again, specificity is something that is very often taught as being one-to-one for a given enzyme. And so in this case, what we have, the first type of specificity, again, we're going to have a spectrum here. The first type is the most specific. Okay, so absolute, if an enzyme has absolute specificity, what that means is that the enzyme has, of course, only one substrate. It will work on only one substrate. And so absolute specificity, if an enzyme displays this type of specificity, it is the most monogamous in that sense, and right along those lines, it's also the most rare. Okay, so you don't get a lot of enzymes that display absolute specificity, actually. It's very useful for organisms over the process of evolution to be able to use one enzyme for multiple purposes. And so you'll see some examples of that later, especially when we get to metabolism. In fact, we already saw one example when that enzyme in glycolysis, one of the intermediates in that was 2,3-BPG, and that's actually used to stabilize your T form in oxygen binding. Okay, so that's really not it working. That's really the process of the enzyme lending itself to more than one end, but it's similar to what I'm talking about here. So with absolute specificity then, and again, this is rare, so almost always if you have absolute specificity, you're going to be what? Of course, the lock and key model. Okay, so this is why this is overlapping with what we just talked about. So for this type of specificity, the enzyme binds one substrate and one substrate only. It is the love of its life. Married 70 years, you know, met in high school, still dating kind of thing. And that is highly monogamous there. So yeah, I wanted to give them some privacy. They can go get a room when we move on and talk about our next type, which is group specificity. So we're going down in restrictiveness here in our specificity level. So absolute's the most restrictive. The next level is what's called group specificity. In group specificity, the enzyme, instead of recognizing just one substrate, recognizes a certain functional group. Okay, so this is a very interesting kind of specificity. So in this case, I've shown the substrates as all being different in their detail and in their shape, and yet they all contain an aldehyde group. And that aldehyde group is all the enzyme needs to be able to bind it and work on it. So the enzyme, this enzyme displays group specificity. Now, it doesn't have to be an aldehyde group. In fact, this we're going to talk in class about alcohol dehydrogenase, and that enzyme displays group specificity, and what it needs is a primary alcohol group. In this case, this is what I've drawn here. This enzyme is looking for a aldehyde group, so this would be aldehyde dehydrogenase, and is an example of this kind of enzyme that is actually looking for that specific group also. So any of these substrates would do, but they must be of a certain type here. Okay, so we can think about them kind of like a harem idea, where this enzyme has a bunch of different loves, of course, but he's married to all of them, or he's got them available, but they all have something in common, and so this is, of course, more promiscuous, certainly not monogamous, will have multiple substrates on which he acts. Okay, so we definitely want to get him a blankie so that they can cover up and go get a room. Okay. All right. The last kind, this is the last type of specificity, is the linkage specificity. This is the Jersey Shore. This is the crazy. This is the promiscuous kind of enzyme. All this enzyme needs, if you have linkage specificity, is a certain type of bond. So not even a specific functional group, really. You need a specific type of bond. And so this player here can work on, I've drawn like just cartoons of proteins here. It can cut up proteins. All it needs is the peptide bond, in this case, that it can cleave. And it will run right through the protein. We already talked about specific proteases and the way they work, and trypsin and chymotrypsin and elastase and all those that you learned. And they will recognize and cut peptide bonds. Now, there's additional specificity that's provided for the given enzymes. So remember that trypsin only cuts after the positively charged groups, and things like that. That's additional specificity. But what it's recognizing and cleaving, what it's working on, is actually that peptide bond. And so you end up with a bunch of broken hearts on this side, and there's not a blanket big enough. Yeah, we're not even going to talk about what could be going on there. A lot of broken hearts going on there. Okay? All right, let's move on. The last kind of specificity is actually different. It's kind of unique. In fact, well, it's not kind of unique. It is unique in that almost all enzymes demonstrate this kind of specificity. So it's called stereochemical specificity. And what it involves is, of course, enantiomeric selectivity. So we all know, hopefully, what enantiomers are. You have the R form, you have the S form of these guys, and they can all they can be present in different ratios. If you have equal amounts of R and S, you have a racemic mixture of those enantiomers. Okay, so you remember, I hope, that enantiomers are mirror images of each other, right? So if this is our substrate that is in the R form, and this would be the one in the S form, right? So they're mirror images of each other. You have a chiral carbon here, and then, of course, any chiral carbon is going to have 4 different groups attached to it, and that generates enantiomers. Okay, now this blue over here is representing the enzyme binding site. Okay, so the the active site, okay? But instead of looking as though we have opened up the mouth and we're looking into the mouth of that enzyme, okay? So hopefully you can see here that if we had this R form of a substrate that was going to try to bind to this active site and match up the red circle with the red ball, the red rectangle with the red rectangle, and the pink triangle here, then what you would do, this R substrate would bind actually very nicely in this active site, because the positions of those residues that are going to interact favorably with this substrate are positioned in that active site in exactly the right place for this enantiomeric substrate, this R form, to bind into that active site and then be converted to product. Okay, so hopefully you can see how that R form is a good thing and results in happiness there. However, if we took the S enantiomer now and we try to put that in the active site, it will not match up. It does not fit correctly. And that's because of the spatial orientation of those groups. Even though they're the same as the R form, they're positioned spatially differently. And so they do not match up to the active site groups that they need to match up with in order to bind favorably. So almost all enzymes, and receptors too, not just enzymes. So receptor binding we're not really talking about here. We're sticking with enantiomers, and we're talking about enzymes, and enzymes catalyze reactions. So we're talking about that kind of substrate binding there. But if we were talking about like a lot of drugs, in fact both of the drugs we're going to talk about in a second actually involve ligand binding to receptor, and that also will demonstrate very clearly stereochemical enantiomeric selectivity. Okay? All right, so I hope that helped you understand what I mean when I say that.